Hello and welcome to this video about proofs in linear algebra. In this video we'll slowly study the proof of this theorem in linear algebra and in vector spaces in particular. It will take a while to explain it. This proof is very reliant on previous theorems and uses English sentences a lot rather than math symbols, but I'll try to explain it all as clearly as I can as we go along, and write out math symbols to match the English sentences when I can. I decided to call this the dimension proof because it uses the dimension function in the statement of the theorem, which returns the number of vectors in the basis of the given vector space V. Even though the function is never used in the proof again, it returns the number of dimensions of a given vector space, which is also the number of vectors in its basis. So this theorem says that given a basis of V called B here, and B has n elements or vectors in it, then any set with n vectors, and that's a subset of V and that's linearly independent denoted by Li, is a basis of V. If a subset of V is linearly independent and has n elements, then it's a basis of V. So I'll just write it out in math symbols as much as possible. So if A has all of these properties, then it's a basis of V. This theorem is in two parts, part A and part B. Part B says that any spanning set of V with n vectors is a basis of V. And I'll start to write this out in math symbols. And here's part B of the theorem saying that any spanning set of V with n vectors is a basis of V in math symbols. So now to prove part A, I'll just restate it at the top of the screen. We'll start by letting set A be a linearly independent subset of vector space V, and that has n vectors. And A can have any other properties. We're required to prove that A is a basis of V, and to do this we need to prove that A spans V and that A is linearly independent. We know that it's linearly independent because that's given, so we only need to show that A spans V. We'll do this using a contradiction. We'll assume that A doesn't span V and see that it will cause a contradiction, and so can never happen. Then there must be a vector that's in V but not in the span of A. A past lemma, which is a minor theorem, says that when we add this vector to this set A, then the new set is linearly independent, because we're adding a vector that's not in the span of A to A, and A is linearly independent, so that this new set is linearly independent. Another past theorem says that any set with more than n vectors is linearly dependent. The number of vectors in this new set is n plus 1, which is greater than n. So this new set is linearly dependent. I'll just move everything up the screen here to make more room. So we've just worked out that this new set is both linearly independent and linearly dependent at the same time, which is a contradiction. And we got this contradiction because we assumed that A wasn't in the span of V, so A must be in the span of V. This is what we were required to prove, so A must be a basis of V. Now to prove the second part of the theorem, that any spanning set of V with n vectors is a basis of V. We'll start this proof. We'll let A be this vector that is going to be a basis of V according to this theorem. So A will span this vector space and have n vectors. And we can write this statement down with mathematical symbols in math notation. So we're required to prove that A is linearly independent. This will be enough to prove that it's a basis of V, because we already know that A spans V. So we'll prove this by contradiction. We'll assume that A is linearly dependent, and so can't be a basis. So now we'll invoke a past lemma, which is a secondary theorem, to say something about this set A when it's linearly dependent. It says that if we discard a vector from A, then it will still span V. And we'll have a closer look at what A contains. It would contain these vectors x1 to xn. So we'll remove the last vector from A without loss of generality, given by this abbreviation. So this is what A is after we remove the last vector. It's a list of vectors from x1 to xn minus 1. It will have n minus 1 vectors. We can remove the last vector without loss of generality, because we can always swap the vectors about, so that any vector can be the last vector. It just depends on how they're labelled. The vectors x1 to xn can be anything, just as long as they span V. So I'll just move everything to the top of the screen to make more room. So I've just found a contradiction. Another past theorem says that a spanning set must have at least n vectors. But we've just found a set with n-1 vectors that spans this vector space, and this set has less than n vectors, since n-1 is always less than n. So I'll just write this down in math notation. Here's the spanning set with n-1 vectors. And it has less than n vectors, so that it can't span V. This is a contradiction because this set A minus xn can't both span and not span V at the same time. This contradiction came about because we assume that A is linearly dependent. If it is, then A with one vector removed would neither be linearly independent nor linearly dependent, which causes this contradiction. So A must be linearly independent, which is enough to prove the second part of this theorem. But we'll have a deeper look into why it's a basis. So we know that A spans V because it's given or stated in the theorem, and we've just proven that A is linearly independent. And that's the definition of a basis. So A is a basis of V. So we've proven part 2 of this proof, and therefore the whole proof. So I hope that you've found this video to be helpful and educational, especially if you're studying it in school or university. Please click like and subscribe if you did. Feel free to share this video, and feel free to write any helpful thoughts in the comments. And thanks a lot for watching.